So here we are, we're going to be looking at module number 4, which is keys and couplings and actually seals as well. And I'm going to take a peek at our learning plan. And you're going to notice kind of some of the familiar parts that we're used to. We have a PowerPoint that we're going to be working through. And then there's also an Excel spreadsheet that we can utilize if you so choose for the homework that's assigned. Now, going back to our module, kind of making sure we kind of know how this is structured, you'll notice that there are practice problems that you're going to be submitting. In this case, there's only one. Okay, so we'll be looking at example 11.1. We will use the spreadsheet to kind of demonstrate how that works, and then you can use that for your submission. Don't forget part 3 of our practice problems. There are a couple of questions here that I'd like you to answer. And then if you forget, sometimes students will say to me, oh, I forgot to add that with my original submission. You can always add it in the comments for that assignment. I can see your answers there. So it's totally fine. I want to keep these informal, but I want them to be a little bit thoughtful. Okay. So those are there. And then you'll notice that assignment number 4 corresponds to this module. And when we click there, there'll be a PDF as we're used to. And then this will be the list of problems that you'll have to do, to apply what we learned. And we'll be talking about those kind of after we go through everything. So first things first, let's open up that PowerPoint, which is in PDF form. And I'm just going to open it up here on my screen, and we'll start working through the different sections here. So first, looking at learning objectives. So in this chapter, there's quite a bit of information in this chapter. The parts that I'm going to go over in detail are going to be the keys, sizing the keys, looking at material for the keys, incorporating into our designs, making sure we get the correct length and what the conditions are and the things that we have to be aware of. Then there's going to be more fastening elements to shafts. So not only do keys go in shafts, but there's seals and retaining rings. And then when we want to transmit power, there's going to be different types of couplings and joints and stuff like that. I'm not going to be able to cover that all, and I don't have the intention to, but what I do want you to do is look to the remaining portions of this chapter, and I've got questions assigned at the end for you to explore those answers. Okay. So, so the last part of this, this chapter, you're actually going to be kind of on your own, if you would, and then, and using the homework problems to, get the answers to the questions. So, so let's go to keys to start off with. That's the beginning, and that's really the bulk of the chapter that it's concerned with. So a key, not to open a door, right? A key is going to be used in, it's a machinery component that's going to be placed at the interface between a shaft and the hub of a power transmitting element for the purpose of transmitting torque. So a key is going to be strategically placed so that, I think it's on the very next, oops, I think I gotta go a little bit further. This one right here. So I'm going to zoom in. A key is going to be specifically placed so that it's going to overlap between the shaft and, in this case, a gear. Okay, so it kind of is going to be in between here. So the shaft is going to have what we call a key seat. So there's going to be a groove that's going to be machined in there to accommodate the key to sit down in there. But the key is going to be tall enough to extend over the top of the shaft and be up into the actual hub / of the gear, but the gear is going to accommodate it with what we call a key way. Okay, so on the top, there's going to be a rectangle, and on the bottom, there's going to be a rectangle, but my square key is going to be in between. So now when this shaft rotates, the gear is going to come along with it. Or if the gear is going to be transmitting torque to the shaft, as that gear rotates, the shaft comes along with it. Okay, now, so the main thing is that it's going to transmit torque. The second thing that it can be used for, which is used very often, is that it is going to be the limiter in the assembly, meaning if we all of a sudden get a jam or an overload, the key is designed most often to be the weakest of those 3 elements. Okay, meaning it's weaker than, or it's going to fail before the shaft and it's going to fail before the gear. Why do you think that is? To prevent further damage. this is what a key looks like. It's a rectangular or a square piece of metal, cut to size, done. Very inexpensive to create and produce and to, just kind of come up with. A shaft, on the other hand, now this is a pretty simple shaft that we see here, but it's going to involve, a number of operations to get things to the right sizes, and it's going to be a heck of a lot more expensive and harder to replace than what a simple key would be. Same thing for a gear. If you're not a gear manufacturer, you're going to have to actually order another gear, have to have it on hand. You're going to have to put that keyway in there and get it into the place where. So just as Jesse said, it's there to prevent other damage to more expensive, harder to change out elements. Okay. So a key, as simple as it is really important to the design, especially when we're transmitting, when we've got gears and V-belts and shivs, the elements that we've actually just recently been talking about here in this class. Okay. And then shafts are going to be coming up very, very soon for us. So, so we're going to be looking at sizing keys. I'm going to scooch back just a little bit here. So it's a machine element that's going to be placed strategically to transmit torque. It can be demountable to facilitate assembly and disassembly of the shaft. We're going to look at some arrangements of keys that allow us to actually pull it up from the side without having to disassemble everything. Okay, so there's some options there. And then, as I said earlier, it's going to be installed in the key seat on the shaft, and then it's going to have to accommodate the keyway on whatever other element, the torque transmitting elements, whether it's a gear, a shiv, a sprocket, a pulley, that it's going to actually be in engagement with. Now, there are different types of keys. The most popular one is going to be a square or a rectangular parallel key. Most popular one. That's the one that we just saw a little bit earlier. And that's the kind we're going to size here in class. But there are a couple of different other types of options here, and we'll talk about those. Okay. So first and foremost, let's look at parallel keys. Parallel keys get their name from all sides on them are parallel to each other. So they're simple rectangle or square cross sections, and then they're made to be the length as long as they can possibly be to accommodate whatever the hub or the size of the element that we're looking at. When we look at a key, the W is going to be the width, the H is going to be the height. In a square key, obviously those two dimensions are going to be the same, but in a rectangular, they're going to be different. Okay, so the width is going to be across the widest part and the height is going to be the shorter part. Now, when we are using, why we would use rectangular or square keys. So we usually start with a square key, but if we have larger, bigger, bulkier applications, we're going to go to a rectangular key because there's more shear area across. Secondly, we would look at a rectangular key if our hub on our gear seems to not have a lot of meat, if you would. I need a lower profile so that I'm not taking too much material out of the hub of the gear. Okay, so that's the other reason. But we're going to be sizing for squares because that's, again, where you start, and it's going to be 98% of the time what you use. Okay. Now you'll notice here that we can have rounded ends, as you see on the ones on the front here, or you can have simple square ends. Okay, really doesn't matter which kind. So so the configuration would be up to you as the designer. Now, to determine what the standard size of the key is going to be, meaning the width and the height. I'm going to zoom in here on this chart. This is found on page 473 if you wanted to look in the book. This is table 11.1. And this is key size versus shaft diameter. So before we can even determine what is the size of my key, I have to have a shaft diameter in mind already. So shaft design has to be done first. I know we're not doing it in that order in this class, but shaft design, I think it's going to come very next. So I think it's the next learning plan or the next module that we look at. So, so we need to know our shaft diameter that we're going to be using in that area where we're going to be putting the key. Once we know what that shaft diameter is, now we can size our standard key. So you'll notice that they give the nominal shaft diameter. The first column is over in inches and to include in inches. So as we go down here, I'm going to try to find if I have a 1 inch diameter shaft, I want to find where it's going to land. So it's over 0.875. but it's up to and including, so in that range, it's less than 1.25. So this is going to be the row that I'm going to find a 1-inch diameter for my shaft. Then I go over. You're going to notice that over on the right, the width of my key, standard key width, is going to be 1/4 of an inch. So for a square key, the 1/4 inch is going to be the height as well. Okay, so anything within this range using the over and to include are going to be a 1/4 inch square key. Now, if we go down further, you're going to notice that the size of the keys go up. The size of the keys go up. So, it's very easy to kind of figure that out. Now, that is a standard across the board. So whether you're looking in the machinery's handbook or you're looking online, these are going to be just, that's where you start. Okay. So, so you first have to know what your shaft diameter is. And then based on that shaft diameter, you pick your key size. Zoom out a little bit. Okay. Materials. Now, as we said earlier, the most common application for keys is to be the weakest of the 3 elements. So if my torque transmitting element or the rotating element, like a gear, sheave, pulley, or a sprocket, and then or the shaft, and then I've got my key. Between those 3, the key is most often going to be the weakest of. But sometimes it doesn't have to be. So very common materials that we're going to use are going to be just kind of plain carbon steel. 1018 is a good place to start when that's the case. But you'll always have to check what the material is that you're using on your shaft, what the material is that's in the element that you're going to be rotating. And then you want to compare, because if the intention is for the key to be the element that fails first, you have to ensure that, right? We have to make sure. Now, the key length, we're going to be solving for how long that key is going to be. And that key length, the minimum key length, is going to be calculated through an equation. We'll talk about that in a bit. And we're going to use our Excel spreadsheet. Again, not complicated, but we have the Excel spreadsheet there for us. Once we know what the minimum key length is, then we make it as long as the hub is going to accommodate, just so it's not like rattling around in there. Okay, that's all. Let me see, plain carbon steel. So materials, really, you can use anything for key material. Plain carbon steels, when we've got like the type of machine elements that we're dealing with, is usually going to be the first go-to. And there's actually, if you go to, for instance, a Ryerson or a Central Steel, they are going to have key material, like it's key stock, okay? And it's going to be this 1018 plain carbon steel that you can get. And then there's other alloys that you can use as well. And based on their yield point and their compressive strength, they would be viable options too. Stainless, if you're in the food industry, you may need to consider that. Non-ferrous materials and also plastics really could be used. I mean, any materials, as long as, however you're designing it, it's going to be that first to fail within reason. You wouldn't want a plastic key if we're using a steel shaft and a gear, just because it could be failing 10 minutes into the operation. So you just want to use your common sense. Selecting materials used for keys. So here's a list of, materials that are common with the 1018 cold roll steel right up here at the top. The 2 things that we're going to be interested in are the tensile strength and the yield strength. Now, you guys didn't have me for strength of materials, and I didn't teach here at WCTC, but yield strength. Tell me about yield strength. What do you know about yield strength? Impress me. Well, not quite. It's before. Remember, the yield is right when it's going to start, like it's permanently deforming and it's not going to go back. It's not going to bounce back. So the tensile strength, though, is going to be now that highest point on the curve where I'm done, right? Now, when we are designing, do we want to be above or below the yield strength? Always below, always below. Yield is considered failure, okay? And it's considered failure because what happens is as you pull that apart a little bit and it doesn't bounce back anymore to its original shape, we've changed the internal grain structure. It's done. Like it's not going to perform anymore. Even if we physically can't see it or it kind of looks like it's still doing okay. Internally, we've changed it and it no longer has those properties that we need. So we always have to be below that yield point when we're designing. So it's important to know that. So The yield point, which for all practical purposes it's a failure. We're done. That material is not going to perform anymore. We don't see failure until we actually see it rupture, right? It's gonna neck down and then finally it'll pull apart, but it's failed before that. It no longer has the integrity that we would be expecting underneath that yield point. So when we look here, that yield point is going to be the number that we're going to be using for our calculations. Okay, we want to know what that yield strength is, because if we get all the way up to the tensile strength, that highest point on the curve, we're already in trouble. Okay, already in trouble. And then you'll notice that there's some other ones here that have different values. So like I said, really pretty much any material, knowing the yield strength, you can use as a key. Okay, and just depends on how you want to, put it in there and what the other materials are that are between it. Okay, or that it's between. Stress analysis to determine your key length. There are two modes of failure for a key. It's going to be shear across. I'm going to peek ahead here. Oh, shoot. Okay. It was so good. It had the illustrations in, but now we're going to look over here. So on page 477, okay, the two modes of failure are identified up here. So you'll see that in the first case, we're looking down the axis of the shaft and we can see the key. Half of it's down below into the shaft key seat, and then the other half is up into whatever this is, whether it's a gear, a sheave, a pulley, a sprocket, and that's up into the top. So as this rotates, you can see they're going to rotate at the same RPM. Okay. Now, because the shaft will be pushing in the opposite direction of the torque transmitting element here, for instance, we have two forces that are opposing. And the middle area there is in shear, right? Is it in shear? So that's the first mode of failure that we can have on a key. And that's usually where it does. It's going to fail. The other part is going to be the compressive stress or the contact stress, or the bearing stress is probably what it was called in your strength of materials class. The bearing stress that's going to be along that face, okay? That face of our key. It can fail there as well. So we need to take those two things into account, okay? Now, to determine the minimum key length. Now, like I said earlier, most often the intent is for that key to be the weakest element, okay? But if it's not, you need to determine the minimum length of the key by first calculating the shear, okay? And what that length would be in shear only. Then you need to do a second calculation where it would be, what is it for the compression? And then you compare those two numbers for the minimum, and you're going to pick the larger of the two is going to be your minimum length of your key, right? Makes sense? But in most instances, you are going to be designing so that key is the weakest of all three. And this is the equation we would use then, which would accommodate both the shear and the compression strength. Okay. So you'll notice here that we have 4. That's just a factor. Then we have T, capital T is going to be the torque. Then we have N. N is called a design factor. And if we go up into the design procedure for parallel keys over here, and the design factor is going to be equal to 3 unless given otherwise. This is like a standard industrial application. Okay. So if you're working on, a conveyor, for your manufacturing plant, 3 is a good number. All right. But if you're working in the elevator industry, 3 might not be the number. Okay. It might be something else. All right. So you want to know for your application, but for standard industrial applications, for the most part, run-of-the-mill stuff, like what we're looking at, mechanical design, mechanical engineering, 3 is our number. So that's going to be what the N is. D is going to be the diameter. Okay. W is going to be the width of the key, nominal size, the width of the key, and then the yield strength of that key material. Okay. And that would come then from, which one did you pick? If it's 1018, it's going to be 54,000 or 54 KSI. Okay. All right. So very straightforward. Yes, the diameter of the shaft. Sorry. Yes. Thank you. peek back over here. There's our equation. So design procedure for parallel keys. Number one, as I said earlier, shaft diameter. You need to know what the shaft diameter is, whether that is you determine what the minimum shaft diameter is by doing the shaft calculations, or in these problems, it'll be given to you, okay? Using that shaft diameter, you go to that table and you find what is my size key. So again, if I go back over there, just reviewing how to use that chart, we're going to find our nominal in between these numbers, right? Wherever that is. And then we're going to go over and our key dimensions are going to be right here. Okay. Now I will tell you that the length and the length calculation we just looked at, as well as the spreadsheet that I have, they're based on square keys. Okay. Square keys. And that's what you're going to be using for me. Because again, those are the biggest, the ones that you're going to use most often. So I get my key size. Then I'm going to determine my suitable design factor. If it's something other than a standard industrial application, then you would want to put in something other than 3. Specify your material for your key. 1018 is very common, okay? Or key stock is 1018, all right? But you can use something else if you want to. Then you're going to calculate the minimum key length. And then you're going to specify your actual key length based on whatever the other machine elements are, and we'll see that in our example. So let's take a peek at example 1 in our book. And that is found at the top of page 487, or I'm sorry, 478. 478. Okay. So what we have here is we have a portion of the shaft where a gear is to be mounted, has a diameter of 2 inches. So that's the diameter of the shaft that we're going to be putting a key into. The gear transmits 2965 pound-inches of torque. The shaft is to be made out of SAE 1040 cold drawn steel. The gear is made from SAE 8650 oil quench and tempered 1000 steel. The width of the hub of the gear that the gear is mounted is 1.75. So that's as long as, if you would, that's the bearing, or the key has to be within the confines of that 1.75. So what we're going to do is we're going to go through and we're going to design our key for this. Now, you'll notice there's literally one equation here, and that's very true, but I do have an Excel spreadsheet for this if you wanted to use it. So if you go back to Canvas and we look at our Module 4 learning plan, that Excel spreadsheet is right here under number 4 for you to download if you want to. Okay. Now, again, not a hard calculation, so it's totally up to you. I have mine pulled up here, and I'll plug in the numbers that we have here for our example. So the torque, and just pay attention to the units on the right-hand side. The torque here is 2965. The nominal shaft diameter is given as 2 inches. Now, I need to go to table 11.1 and pick out the width of my key. So I'm going to go back underneath here. Okay. I'm going to go back to table 11.1. It's on page 473. And I have a 2-inch shaft. And you'll notice right here, it's going to be over 1.75 and then 2 and including 2.25. So it's right in between here. So I'm going to go over to the right, and my nominal width and height is going to be a half an inch right here. Okay, 0.5. It's going to be 0.5. The length of my hub. In the problem, it told me the length of the hub was 1.75. And then my key material, we're gonna start with, you know, the cold roll steel, 1018 cold roll steel. And then the yield strength. If you're not sure what it is, they do have it on the chart here on page 476. Okay, table 11.4, 1018 yield strength in KSI. Don't use the tensile strength, use the yield strength. 54 KSI, so that's 54,000 PSI. I forget what I have this in. Yeah. So you want to go 54,000. Okay. And then it computed my minimum key width or key length right here. So this is how long my key needs to be to accommodate that application. Now, the actual key length. We want to bump that up as long as we possibly can. So we want to, first of all, go to a nice number. Right now, our number is 0.65888888 repeated, okay? Just as a note, out in industry, as we know, we're in the English system. So you always want to try where it makes sense to do numbers that are going to go along with our inch increments, whether it's, you know, a 1/16 of an inch, an 1/8 of an inch, a 1/2 an inch, whatever it might be. Because if you don't, they'll kind of know that you that you're new. Okay. You want to show, you know what you're talking about, and you understand the deal. So, so what you want to do is for this one, you would probably want to go up right away to 3/4 of an inch at least, right? But remember, the length of our hub is 1.75. We can make it as long as possible. So I'm going to go back underneath here. We're going to look back at our example, and this is the figure right below. And you'll notice here that my hub has to fit in between. Now they don't have a shoulder, but they have 2 retaining ring grooves. Okay, 2 retaining ring grooves. And those 2 retaining ring grooves are keeping my gear in place. Okay, so in between there is where my key has to fit. It cannot, and any machining required to put it in place cannot go outside of those bounds. Reason being, and it'll make more sense when we do shaft design, our shaft design takes into consideration stress concentrations. If I go out of the confines here with any machining, like with the radius of my mill, I now have a multiplication factor of 2 stress concentrations, and now my diameter has to get much larger to accommodate that. Okay, I only want to have 1 concentration factor at a time when I have it. So I cannot go outside of that. So that's why, as you look at the top here, okay, notice that the radiuses are within the confines of how wide this is. All right. Now, this is someplace I differ from the book. Okay, because they're making the rounded ends here of their 1/2 inch wide key to be the exact size of what it would fit down into. If your pocket on your milled, key seat isn't the exact same size as these radiuses on either side, it's not going to fit in there. All right. Or it's going to kind of, sit down in there and it might not seat decently. So what I always saw typically, we never did it this way, but we would mill the pocket to the ends, but our key would stop at the flats. So we would have a rectangular key square on the ends, and then it would sit in between the centers of where you ended each side of the pocket. So the pocket has the radiuses. Okay, you're going to go down with an end mill. You're going to pull back out the length of your key, but your key is literally only, in this case, 1 inch long, not 1.5 inches. Does that make sense to everybody? Okay. That's how I want you to think about it. Think about manufacturing process, because even making the key with the radiuses, why? That's extra cost that's induced, right? For a part that is designed to fit.
I mean, they have keys that are made that size. They're typically called French, like keys.
Yeah.
Aviation.
Okay, you can, yeah, and you can put them in there, but then you have to be then hyper aware of the radiuses that you put on there so that you don't, hang up on that part. So typically, if we're making our own keys, but if you're buying them, yeah, you could do it that way too. Good point. But if like I said, I was on my applications when I was out in industry and doing like packaging equipment, high-speed packaging equipment, we just made all of our keys, and then we would just cut them to length rather than putting the radiuses on. So the actual length then would be 1 inch, and we're still meeting the minimum requirement. So if we go back to our spreadsheet here, our minimum was 0.6588. Actual key length here would be, in my case, I would design that to 1 inch. Okay. And then you'll notice down here, there's a design summary that fills in. And then the one thing that doesn't is the key material. So if you want to do an equal to and go back up here, you can do that. And then we are all set. because I would make this so that I would mill the pocket 1.5 inches on the radiuses, but now I would actually make my key, I would cut it off flat rather than having the rounded ends. And I would make my key just 1 inch to fit between the centers. Well, you tell me. Where does that 1.5 inches come from? The width of this key is 1 inch. So if I had an end mill that I would plunge down in here to make my key, what is its radius going to be? 1/4 inch, right? 1/4 inch and 1/4 inch. Tell me why. I actually just said it. Why can't I run it the full 1.75? What will happen? How far out will my radiuses go? The radiuses are going to go outside and they're going to interfere with the retaining ring. If they go into that retaining ring and we do shaft design, we are now have a multiplier for our stress concentration. And now my diameter of my shaft has to get a lot bigger to accommodate that. You can't go out into the confines of with any manufacturing process or any part of your key. You're the designer. You have to just make it smaller. You have to, number one, be able to make your key at least that long. And then number two, ensure that as you design, that you don't go outside of that. Center it. You're just gonna probably find the center of 1.75. Make sure that you have a little bit on either side so that you don't, with your manufacturing process, go outside of that. And that's all you have to do. You're the designer. And then you're going to, dimension it along the length of the shaft. The point here is you can't go outside the confines with the manufacturing process or the key itself, either one, outside of the 1.75. So if you want to make your key 1.5 inches, and you're gonna plunge down with a 1/2 inch or a 1/2 inch diameter mill, you're not going to be able to do it. You're going to be in trouble. Okay. Does that make sense? Because remember, you're going to have a key that's going to be sitting up here, right on either side. Okay. So you can't mill into, because your retaining ring groove is here and it's here. You can't mill into that. So my point is your key won't be as wide as the hub. It has to be within the confines, including the manufacturing process, less than the hub, right? Okay. So you as the designer get to decide that and ensure that. Okay. Now, then I think, let me look here. I think we have everything filled in down here. So make sure that you put in your actual and then make sure that it populates down here. Then. Oh, I must have gone out. Hold on. I've got to go back. Oopsie. I want to get back to my PowerPoint. And here. Procedure for the keys. And then design the key. So now the rest of our chapter is the other methods of fastening elements to shafts. So you're going to come across pinning, set screws, taper screws, press fitting things on. You're going to be finding retaining rings in here. They're going to have applications and explain it. And you're going to have questions in your assignment that are going to associate with those. Those are the ones I want you to kind of look at and I want you to investigate. This part of the chapter becomes a lecture that I would do to you. And I feel like that's something that you can kind of put your nose in the book and find, good answers for. So let's take a peek at the homework that you have assigned. So as we look here, number one, practice problem. You want to include the screenshot for the problem that we just did. And then you'll notice that there are a couple questions, part 3 here of the submitting instructions. So, so you're going to imagine a classmate is absent from class when we did module 4. How would you explain module 4 to him or her in 25 words or less? Like, what did we do? Did I miss anything? What did I miss? And then your favorite part of module 4 was what? Okay. And then we'll look at our assignment. So assignment number 4. Click on here. These are going to be the end of the chapter things I want you to do. So if we go to the end of the chapter, we've got 11.1. So page 507, page 507. So, oh, actually 506, it starts on the second column here, 506. So 4 problems, 1 through 4 and 7, and you've got problem 1 and 4. Okay, so for both of these, determine the required key geometry, length, width, and height. Use SAE 1018 steel for a key to satisfy the design to be achieved. If not, use a higher strength key if needed. Unless otherwise stated, assume that the key is always going to be the weakest when compared to the shaft material and the mating elements. Oh, that just reminded me. Let's go back to 11.1. I'm so sorry. I'm so sorry. This is critical to the design. I want to show you where you need to compare your strength of your materials or your materials back to the key to make sure it's the weakest. This is important. Remember, this equation is when the key is the weakest, but if it's not, then we have to use those other 2. So to determine if it's the weakest, you need to compare the material of the gear and the material of the shaft. We got to compare the yield strength of each of those. So to find that, we find those in the appendix. So SAE 1040 cold drawn steel. We're going to go to the back of the book in the appendix, and they have the material charts. So it's SAE 1040 cold drawn steel. So on the first one here, these are carburized steel. Charts. The basic one. Yeah. So on page 787, 1040, and this is appendix 3, 787, 1040, cold drawn. And we're going to go over to the yield strength. So for the shaft, it's 71,000. I'll wait till you get there. So page 787, appendix 3, 1040 cold drawn steel. The yield strength is 71,000. So our 54,000 for our 1018 is less than the shaft. Okay. So we're okay on that one, but now we've got to check the gear. So did everybody see where this is? Appendix 3. All right. The gear is 8650 oil quenched and tempered to 1,000. And that's going to be steel. And if we turn the page, we're going to find that on page 788, still appendix 3, 8650 oil quenched and tempered 1,000. And we're going to go over to the yield strength column in KSI, and this is 155,000. So 54,000 is less than both of those. I'm so sorry. That's like important information. And I want to make sure you know to look in the appendix for these numbers. Okay. Then going back to our problems, kind of critical. I got caught up in the spreadsheet. And what it says here is, unless otherwise stated, the key material will be the least of, or the weakest of. So if they give you materials for either the shaft or the gear, you need to look those up in the back of the book to ensure that your material is less than. Okay. So you're going to have number 1 and you're going to have number 4. Okay. And number 4. And those two, you can, like I said, it's a 1 equation thing, but then you've got to put the other information in. The spreadsheet kind of organizes it nicely. So you can choose to use a spreadsheet or you can do it by hand. Totally up to you. So those two are going to be the key. And then number 22, 23, 24, 25, and I'm sorry, and number 20 down here. These are going to be the ones that you're going to capture from finding them in the reading. Okay. So I encourage you to read the chapter. Mott book is picked because it does a nice job of explaining things. I think it's one of the very few textbooks that you're going to have as an engineering student that is going to actually be something you can sit down, read, and understand. Engineers aren't writers, but Mott does a fantastic job. Okay. So I encourage you to do that. But I realize that you may not be a reader. All right. But this is my way of getting you kind of into the textbook. Okay. So if we look at the assignments kind of back here, you'll notice that the first two are worth 10 points because they're kind of the calculating ones. And then the last ones are worth 3 points each. I always look back when you give an answer. I want to make sure that you are completely giving me an answer. I look, did you answer, was there 3 parts to it? Was there 1 part to it? Am I getting what you want? Write me a complete sentence too. You guys are college students, all right? I don't want 1, 2 word answers. You might say, well, it didn't say that. So, let's communicate. All right. So any questions about this assignment? You don't have to write a book or do research. I'm just asking you to write a complete sentence. Okay. All right. Then the rest of the time is yours. So we're at 3 o'clock right now. Then we have about, I don't know, about 45, 50 minutes left. And you can use the rest of the time to work on the 2 sections that we went over today.